Okay, Assalamualaikum and hi again. So now we go to chapter 1 part 2. Okay, so this is a continuous part from the previous part. Right, we are still in the same chapter 1. All right. Okay, so we will go to reaction kinetics. So you will see a few terms, a few new terms, which is reaction kinetic, reaction mechanism. So we will, okay, in the first few sections in this chapter, so we will learn on these terms so that you will familiarize with those terms, and then we go the application of these terms into the some of the reactor design, right? So what is reaction kinetics? Okay, so definition is to the meaning of reaction kinetic is a study of the rate, okay, your reaction rate, okay, at which chemical process occurs, and also it will involve the reaction mechanism. Okay, the usage is to size the reactor used to determine the reactor dynamics. Okay, so reaction kinetics is associated with reaction rate, okay, reaction rate constant. So in this chapter, you will need to derive the reaction rate, okay. Rather than in CRE1, okay, you can assume the rate is either elementary or non-elementary. But in the CRE2, where it applies to producing or deriving reaction rate for a solid catalyst, you will need to know step by step on the reaction kinetics and how to apply the reaction mechanism. Then only you can derive the reaction rate law. Okay. So, the importance of reaction kinetics can be described in this diagram. So, in a chemical plant, you will have a reactor, which is the heart of a chemical plant. Okay. So, in order for you to design a reactor, the first thing you will need to have a reaction kinetic, which includes your reaction rate. Right. So bear in mind there are some chemical plant that don't have reactor, such as like the petroleum refinery. Okay, in petroleum refinery there are more separators, distillation columns, right? Okay. So these are the historical development of kinetics in relation to catalyst. So here you see some of names. Okay, so you will see Arrhenius equation that you have learned. Okay, and then this is, all this is associated to development of kinetics. And then in this chapter you will see those Langmuir and also Hirscherholt. Okay, so you will see a lot of these names in this chapter, okay, where we will use their theories. Okay, right. So the next term is reaction mechanism. What is reaction mechanism? Okay, so reaction mechanism for a solid catalyst, you will see there are 7 magic steps. Okay, I call it 7 magic steps. It doesn't mean that you need to memorize it, because it's an open book, right? So you can refer to the book anytime. But it's good that you can, you can memorize it. But the most important part, you need to understand first. So these 7 steps are the steps that a catalytic reaction will undergo in order, from reactant to product. So in this case, you will see that the reactant A will go through the catalyst, will go through all these 7 steps in order to produce B, the product. So the first step would be bulk diffusion. Okay, so this diagram are actually reflecting this explanation, right? So bulk diffusion, also known as external diffusion, okay, it will make the reacting molecules to the surface of the catalyst. So bulk diffusion, if diffusion you have learned in your mass transfer. Okay, so later we will go to deeply what is diffusion, but in this chapter it is important for you to know, okay, understand this 7 step. Okay, the first one is the external diffusion, where reactant A will go to the surface of the catalyst. Okay, and then the second part would be pore diffusion or internal diffusion. Here, when the reactant already arrived at the surface of the catalyst, it will go through the interior pores of the catalyst. This is for porous catalyst. And then at the third step, which is the adsorption. So mostly it is chemisorption, okay, on the surface of the catalyst. Then only the fourth step, you will see the reaction of the surface of the catalyst between adsorbed molecules. So you will see the reaction will only take place at step 4, which is A will be changed to reacted to B. Okay, so at the catalyst surface. Okay, right. So that's why we initially we learn first what is active site, what is a surface area of catalyst. Okay, so the reaction needs to occur on the catalyst surface so that A reactant will turn to B product, right? So the fifth step is actually desorption. Okay, desorption of the product. So you have to let go the B. Okay, so let it go, let it go. All right. So this is the desorption, and then again it will go through the internal diffusion. Okay, from the surface of the catalyst to the outer surface, right? And then finally is a bulk diffusion again. So there you go, the product of the catalyst. So in this chapter, okay, in this chapter 1, you will see that step 3, 4, 5 is the important part. Okay, and then in chapter 2, which is chapter 11 in your textbook, will discuss specifically on the external diffusion, while chapter 12 or chapter 2 is discussing about internal diffusion. So this chapter will focus more on 3, 4, 5 by assuming that step 1, 2, 7, and 6 is rapid. All right, so these are the steps that will make as the rate limiting step. So what is rate limiting step? I will explain to you later. Right. So again, this is another, another diagram that showing you how the reactant travels into the catalyst and produce a product. So this one showing the arrow is actually showing you A will absorb on the catalyst surface. All right. So it will go through the pore. So this one, what we call it boundary layer. If you remember last time when you learned in mass transfer, heat transfer, there's a film, that a resistance to the heat or mass transfer. What we call it boundary layer. So the thicker the boundary layer, the more resistant it goes, right? Okay, so these are the pores of the catalyst. So the reaction will take part in the pores. Okay, this is actually to describe in a porous catalyst. So non-porous catalyst is a different mechanism, right? So here they zoom out is actually what the pores contain. The pores contains of macro pores and also micro pores, right? Okay, now we go to the rate limiting steps, or known as rate determining step, RDS, right? So what is rate determining step? Okay, RDS. In a kinetic scheme involving more than one step, okay, those 7 steps just now, it may be that one change occurs much faster or much slower than the others, as determined by relative magnitude of the constant. Okay, so in such a case, the overall rate may be determined almost entirely by the slower step called the rate determining step. Okay, so I go back to the previous slide. So remember this 7 step. Okay, so let's say we're focusing on step 3, 4, 5 because that 1, 2, 5, 6, 7 is a rapid step. Okay, so in the slide just now, RDS means the step that is the step that have the slowest step will determine the rate of reaction. So among these 3, 4, 5, step 3, 4, 5, we need to choose which one, okay, or we need to identify which steps is the most slowest step, okay. So the most slowest step will determine your, your reaction rate, or your reaction rate step, okay. So that what we call the rate determining step, right? So for instance, okay, you see in this figure, you wanted to, to pour the liquid in the beaker to this funnel. So what okay, so what how can we, we can speed up the process of filling the bottle or filling the flask, okay. So maybe is it, if you pour it faster, will it, um fill up the flask faster? No, right? So it is actually, what is the, resistant, the most resistant step in this figure. So it's actually, if you can provide a bigger, bigger neck of the funnel. So meaning, if you can provide bigger neck of the funnel, so the liquid will go through the flask faster, isn't it? So that is the example of RDS, rate determining step. All right. So in this case, the rate limiting step, which step has the largest resistance? So let's say just now I said 3, 4, 5. 3 is step 3, absorption. Step 4, surface reaction, and the step 5 is desorption. So actually, in order for the, for the electric to complete the circuit, so it needs to go those resistance. So which one will take the hardest, the highest resistance? So you need to solve that part first, okay. Then only the electric circuit will, complete, right? So for RDS, okay. So type of limitation, so external diffusion, internal diffusion, surface reaction. Okay, so this one, okay, external diffusion just now is step 1 and also 7. Internal diffusion step 2 and 6. Surface reaction is step 4. Okay, so these are the parameters that, that can influence, that can, whether increase or decrease your reaction rate. So velocity V, particle size, okay, D, temperature T. Okay, if you look here, for the RDS, or the step limitation is due to external diffusion. Yes, you can, you can increase the reaction rate due to the external diffusion by having higher velocity. Particle size will be affected, the reaction, and also temperature. But for step that involving internal diffusion as RDS, velocity, changing the velocity will not affect it. Okay, but particle size and temperature does affect. But if your reaction is actually surface reaction, only temperature will give effect. Alright. So diffusion controls reaction rates are few. Diffusion limitation could be avoided by adjusting the velocity and catalyst particle. These are the summary. However, 75% of the reactions are actually controlled by surface reaction, which is good, rather than the diffusion. Later you will see why did I say like this. Okay, chemisorption of reactants and desorption of product could also be rate controlling in a few cases. So it absorption will be the RDS, but very okay, only a few of the reactions, right? So I'll stop here for the part 2. So we'll continue in the next part. Thank you. Any question you can ask me in the group, right?